This is pretty simple. We're doing some improvements. I see. Gibbs. What is Gibbs? Gibbs, free energy, thermodynamics. Gibbs, free energy.
Professor Dave here. Let's learn the laws of thermodynamics. He knows a lot about science stuff. Professor Dave explains. The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept.
Hey, how you doing, man? Can you hear me? Hello.
Hello, good evening.
Hey, how you doing, man?
Yeah, doing okay.
That's good. Yeah, I'm glad that you were able to get my message on time. So like I did change that right at the nick of time, but were you able to like this assignment was pretty long actually. Were you able to like finish it?
You know, this was T6, right?
Yeah. I had a question about this. Are you guys doing all the critical thinking and then the exercises?
The critical thinking is what's going to be worked on, like to be turned in, but the exercises are so you can prepare for the tests.
Okay. I did both of them. I did all of the critical thinking. The exercises, most of them I did. I should be able to get to like I said, it's pretty long. Like there was like 10 and 12 questions.
Yeah, and I mean I have also the older, like the very first section is even longer. It's about for
Okay.
G1, that one was a good 20 pages or so.
Was that about first law? I know this one's about second law.
Yeah, that was for kinetic molecular theory of gases,
Okay.
and like average speed and things like that.
Okay. You could probably if you want to share that one, I can take a look at like does the professor usually give you the answers for they're kind of a lot of the questions here. It seems like this book is a more research oriented. Or is it? It seems old. What's this? What's the book called?
It's called Physical Chemistry, Thermodynamics, and Chemical Kinetics.
Okay,
And it
that's like
is
a lot of one thing in like usually it's like separated.
yeah, this is like the custom edition, but it says list of titles and it says Physical Chemistry, a guided inquiry, thermodynamics.
Okay, all right. Yeah, it's not that bad. It's good that they actually broke down because a lot of it is just doing the working with the equations for second law and first law.
Yeah.
And then the critical thinking really has a lot of derivations, which I feel like it is important. For one, it's good, and then the exercises, that's where you finally tackle like, okay, here's a chemical equation. Give me the delta S and delta D.
Right.
Yeah. So which ones did you try? Because I did look at like T6. I think it says T6 critical questions. And I saw some of you had like answers already in there.
Yeah, I kind of got lost at that point. So
Okay. Let's just look at the concept first for like second law. So after like talking about you probably already got a good grasp of the first law, right? This is just energy, this part right here. Yeah. It's just this guy.
Yeah,
energy, work and heat. Yeah.
Mm-hmm.
And then like there's a bunch of equations there for like there's the work and then the heat and then conservation, and it just all in like just working with first law. And you can definitely just to review about the energy is just the ability to change work, right? It's like in essence, it's like qualitatively thinking about it.
Yeah.
And then work and heat are kind of interrelated. The only difference there is like energy being transferred as like mechanically is work, and then thermal would be heat.
Heat.
Yeah. Well, we can do more problems. Like, is there a chapter on first law where I can like take a look at later on?
Yeah, let me see real quick. So let's see here. So there is, okay,
I
cool.
have a really great book that has like a good amount of problems that I can probably send it to you for when you study for the exam.
Okay, yeah, there's a first law of thermodynamics T2. I'll go ahead and send you T2 real quick.
Okay, this I'll take a look at that later. But for this one, so did you hear about entropy? Like, like what that means?
I mean, entropy is delta H. It's the disorder in the system.
Yeah, delta H. We technically call that like enthalpy.
And okay,
Yeah, like it. I'll show you some of the equations later on. But yeah,
would that be then
disorder.
delta S then?
Entropy is delta S. Yeah.
Okay.
So entropy, it's like this. You know, the first law usually for thermodynamics is what's used a lot, and then the second order it's kind of like to explain it. It's not really used a lot. It's more of like if you remember the direction. I don't know if you took fluid mechanics, but it tells you the direction of how the process is. Because like you have these guys, but then there's a reversible and an irreversible. But it tells you if it's like if you have, for example, this guy right here as an example, and you're heating this guy, right? And this is your system, like a cup of coffee maybe, and then you have a surrounding. But then how do you know that the energy is being absorbed or is it being released and lost to the surroundings? Entropy is really the concept or like the second law in essence of thermodynamics that tells you that direction, like whether you're going from hot to cold.
Mm-hmm.
And it's the same thing with conservation of energy, where energy goes from if you're heard of the Bernoulli equation.
Yeah, I think
Probably
so.
in fluid mechanics, where when you have water, water always goes from like high elevation to low elevation.
Mm-hmm.
Same with energy and entropy. It gives you this sense of what is the direction of the process, depending on like a bunch of equations. So that's really how it's used. Like why it's there is because it at least tells us whether like for example, thinking in reality, that this right here, this can't be true, right? Like you have the hot when you leave this open to the surroundings and it's hot. Eventually, after like 20 or an hour, it's not gonna absorb it, right? It's you're gonna lose it. And it's gonna be cold eventually.
Yeah.
Like your system's gonna become cold because because it's of the openness here, and that's why the entropy right here would be positive, and then that's how you know that this process is what happens in reality. Because delta S in here would be negative, which is no. And this is just a bunch of like equations. Usually, this is done when you like derive. I'm not gonna like go to like each individual derivation, but it starts out with a Clausius inequality, which is just this guy. And then obviously you have this entropy and heat transfer, which is disorder plus heat transfer. And then entropy is usually given as delta S.
Mm-hmm.
And then from what I just talked about the coffee that's gonna lose heat from the surroundings, it's because the process of doing this is you always have an increasing entropy where you have this as a like it has to be greater than 0. And then the whole equation here is typically like the delta S, or the entropy of the universe, is the entropy of the system and plus the entropy of the surroundings. And then entropy is just enthalpy, the H, over like temperature.
Yeah.
And then another thing. So those are just the equations. Is how do you know if something is like gonna be spontaneous or non-spontaneous is I think you can use two things. Let me just see, because I did this in. Yep, yeah, you can use two things. You can either assess the Gibbs free energy, or which is this guy, or the entropy itself.
Right.
So if the Gibbs, it's pretty much a consequence. Like if your delta S is greater than or equal to 0, that's when you have spontaneous. But so if this is greater than, it's a high number, but it's a minus sign, right?
Mm-hmm.
So this is going to become negative. So it's the same thing. Either your delta S is greater than or equal to 0, or your delta G is less than or equal to 0. It's spontaneous. And then if this is like less, and then this is positive, if this is delta S is less than 0, which is the consequence is the Gibbs free energy is greater than 0 from this equation, then it's non-spontaneous combustion, non-spontaneous process. I think there's like just knowing that, and then like the way you can explain like different scenarios, and whether this is like spontaneous or the equation itself really inform like, oh, okay, that makes sense. Like, so having kind of like a qualitative view understanding of like the equations, not so much because that's what technically the second law is. A lot of times it's just used as a qualitative assessment. The first law usually is used as a quantitative. Usually like, you have a lot of these equations and you're given, and you have to calculate, heat capacity, the work, and then energy, all that good stuff. And you have to calculate that for first law, but the second law tells you what direction, and then whether it's like irreversible, reversible, spontaneous, non-spontaneous. And I guess this is just another equation, but the enthalpy, the enthalpy is this delta H in our entropy equation is just the internal energy, right? The delta U plus this PV. You've probably seen this one before.
Yeah.
So yeah, like that's kind of like a viewpoint. The equations can expand. I guess once we apply it, I can talk about that. But these are technically the main equations. Okay, I guess did you want to talk about like, because there's a lot of these for like the critical thinking. Some of them are very easy. Like for this first one, how did you feel about this one?
I mean,
What is spontaneous?
it would really just be a natural process.
Yep. Yeah. It's just the
It just happens.
It just happens. Yeah. And then like you could also talk about like the equation. The qualitative equation. Like you can talk about these guys, these two. But what you had is good. So these couple ones, number 2. What do you think about these? It's just a lot of these are just like, okay, you have this S final, right? It's greater than what happens. It's just applying this equation.
Mm-hmm. I mean, if the delta S is going to be greater than the initial, because I mean it's final minus initial. So if final is larger than initial, the total will be positive.
Exactly. Yeah. That's really very simple. It's you just have to compare those two, and then what is the definition of spontaneous that we just talked about?
I mean, it's just, I was just thinking because it was any process. So any process is spontaneous as long as it, I mean, occurs naturally. And delta S is,
Yeah, for it is. Yeah, that's a qualitative
system.
thought about it. But if it's greater or equal to 0, that's spontaneous process. And then I think if delta S is 0, if I remember, it equals 0, that means it's reversible. And then if it's greater than 0, that's irreversible. I think that's what that is. But both of them means it's spontaneous. Like which is the this is the definition, yeah.
Mm-hmm.
Yeah, like I said, a lot of times it's just remembering the delta G and delta S, and then what is reversible, what is irreversible. And then it's just pretty much like, okay, they'll give you these two things, and then okay, if this goes up, this, you know, if this goes up, and this is low, what happens to your delta S total? Like, those are questions that can be shot out like very simple. It's like, okay, as long as you know what I mean is, as long as you know what delta S is greater than or equal to 0 or less than, what that means. I think that's a good good takeaway from like the second law.
Okay.
All right. What about this one?
3, let's see. I mean, it's just the opposite of the number 2.
Yep. Yeah, no,
And
it's
so
like
it's
one.
negative.
Yeah. So yeah, like this is pretty much, so this is going high, and this is going low, and then just applying the equation. Okay, so this goes low, this goes high, and this is negative, right?
Mhm.
So this whole thing should go down, so it's negative. And by definition, is that spontaneous?
I mean, it has to be greater than or equal to 0, so no.
Yeah. So this one cannot, and this kind of, you know, falls directly from our understanding. And what about the reverse? This is a tricky one. What about the reverse?
Reverse, let's see. Reverse process. So, I
So
mean,
when that says reverse, you just reverse the process, the opposite of it. What does it?
so if the initial is greater than the final.
Yeah, and then that falls directly, right? That's going to be greater.
Yes, I mean, it's just the same thing.
If this one is higher, if this one's higher, it's what we had before, yeah. If this, because you're gonna reverse this one, this one would be, that's what it means by reverse. It's not like the reverse. Like, what is the opposite of it? Because then this becomes like final, right? And this is initial, or whatever, however you're gonna look at it.
I don't
Like
know.
that's the way I'm thinking about it. Like, if the reverse is spontaneous, because if this is greater than in the, and then you reverse the process, this one would be higher and this one's less. It's the reverse. It's the opposite of it.
So the opposite would be final is greater than initial.
Yeah, same as this guy right here. It's the reverse. It's the higher one. Yeah. It's a very qualitative thought, but like the process, like, you know, you start out with this guy, the initial is greater than the final, and then you switch that, so the final is going to be greater than the initial.
So then that's just the same as number 2.
Yeah, exactly. That's
If,
what I'm saying.
and if number 2 is
It doesn't ask for the reverse though. But if it did ask for the reverse, it would be non-spontaneous. Yeah.
okay, it did ask for the reverse.
For
So the
number two.
reverse, no, for number 3.
Yeah, for number three, when it's asking for the reverse, it's just like, you just switch these guys. The final and the initial. If it asks for the reverse, you just switch them. This one didn't ask for it, but it's just the reverse of like this guy. So like, what's the reverse of this? It's gonna be S delta S total is like less than 0. And this one, what's the reverse of this guy? The delta S total is greater than or equal to 0.
So it's the reverse for each part.
Yeah. Like,
Okay.
when it's saying reverse, it's not like reverse process. It's the reverse of this. So that's why the reverse of this, the process, is going to be opposite of what you have here, which is, greater than.
So it's number 2 saying larger greater than smaller, but in this one it's saying smaller greater than larger.
Yeah, and this is what's given to you, but then the reverse of that would be you're switching the final and initial. This is the equality sign is the same. However you want to look at it, but that's just what it is.
Okay, so then it'd be S total final is less than S total initial. Or no, it would be S total final is greater than S total initial.
Yep. Yeah.
So in that case, the process would also be spontaneous.
Yeah, it'll be spontaneous once you reverse it. Yeah.
So then 3C's should be yes, not no.
Yeah.
Okay.
Okay, so let's take a look at this one. This one's a little tricky. What about this one?
Okay. So
So now
define when
they're
the
equal.
initials are equal.
Yeah.
So since there's no change, it would be 0 as a sign.
Yep. Yeah, that one's good. Okay.
And then I guess the process
So
should
this is
shouldn't
the
be
give.
spontaneous.
Yeah, this is the given process, and then the other one reverse. And then okay, let me see. So the given process that kind of falls directly, right? Because we have what was it? Well, this right here means spontaneous, right? Greater
Yes.
than and equal to. In this case, we don't care about the greater than, but so it's equal to. So yes, right?
Mhm.
Okay. But what is the reverse?
The reverse would also be spontaneous too.
Exactly, yeah. So this one is like, yo, yeah, that's done. So yeah, just knowing that, and then so even if you just have like, okay, why don't I just switch these? The qualitative aspect, like, okay, yes, it is true, but then what if you just switch these? You don't have to think about it that much, but you know, 'cause they're both equal. So that's why the reverse is also true. It's also spontaneous.
Yeah, no, it would be at equilibrium because it's equal.
Yeah, there's like different like it doesn't really tell you like, oh, I mean that there's different equilibrium, like thermal equilibrium, like chemical, but yeah, in this sense, yeah, because they're equal entropy, then they are, yeah, I guess that's the meaning of it, because that would be equilibrium. And what about, which one is that? What expression? Oh yeah, this one is just what you already know. This is just the equation.
Yeah. So it's just the system plus the surroundings.
Yeah, this one is really easy one. And finally, this one, we're gonna actually apply it in a sense, like qualitatively. Okay. This is kind of just you know, like when you have this hot brick, right?
Mhm.
Yeah, you have the questions already. I'm just gonna look at like the answer. It's pretty much what you put. The system is the hot bricks, right? Which is this guy, and then the surrounding is like the water.
Mm-hmm.
And then so the direction of this, right? Since this is like open, is this way. Same with the cup. This is kind of similar to the cup. It's going from hot to the cold, and then so your system, surroundings, and this is the change, you know, in temperature would be, the system itself will go down because you have the cold surroundings,
Right.
and that's just directly from entropy. If it's greater than or equal to 0, so, and then the surroundings itself would take that hot and then probably absorb it, and then looking at the system, it's gonna lose heat. So you could, you know, you could talk about it in that sense, but with the system and as the surroundings, what happens to the surroundings. So
Well,
what about this guy? I don't know what to see. Let's see. Yeah. So like, is this one what we're talking about here? Is this thermo? Is this first law or second law?
that would be so first law, second law. Could you kind of like refresh me on the laws of thermodynamics again?
Okay. So the ones that we talked about first is first law itself is just energy, conservation of energy, COE, and then you also have like work, right? And
Yeah.
then you also have like heat. These three work here, but the thing is, it doesn't tell you the direction. You know, like this is just calculating what temperature change, what is work. which is like force and distance. Like I can show you the equations later on, but then in essence, the second law is this part right here. Yes, you are changing the temperature, but then it's not really Q. You know, this, like, what I'm trying to say is, like, once you have like a change in temperature and in direction from hot to cold, you're applying like the second law there, because of the direction of hot to cold, which is this guy. The first law is anything that's involving energy, either work or heat, transfer of energy. Which is, there's another question on it, right? This one, the other question is asking about internal energy. So the internal energy is applying the first law, but then if it's a direction, like from hot to cold, it would be the second law. I don't know if that kind of makes sense. It's like the direction of like where your process, you know, the heat, where does it go from hot to cold? That's second law. But when you're just calculating and conserving the energy, it would be the first law. Once we do the problems, it's going to make sense. There's more problems for first law than second law, and then we can technically like categorize them. It's like, oh, okay, this looks like a second law problem, this looks like a first law problem. Like if once I take a look at how you guys do, because there's a lot of problems that I can give, but I want to like kind of like put a boundary on that of like how you guys present it, and you know, how the problems are set up. So it's kind of like similar. So like, yeah, maybe for next time I'll send you the T2 stuff, and then some of these, and then kind of like we'll go. Did you want to go over like first law as well, problems later on before the exam?
Well, this was the material from there was already from the first exam, so I've already
Oh,
taken
really?
one
Okay.
test.
I didn't know that. Okay. How was the exam like? Was it similar to the homework, or?
I mean, it was. I don't really know. I know I didn't do well on it. Really didn't do well.
Okay. That's why we're gonna do our best too. Like, was it qualitative or quantitative?
So I have it actually with me.
Okay. Do you
Kind
mind?
of
Yeah.
kind
Do
of
you
looks
mind
like
like?
this.
Let me see. I can't really see right now. Let me see. Okay, I'm trying to see if I can. Okay, I can see it a little bit. Do you think you can send a picture to me of that?
Yeah. Let me.
Because then that would be I think what would be great is that, you know, because your final is gonna be that and everything else.
Mhm.
I can at least go over the problems that you know that you got a low score on.
Yeah, that was pretty much everything. I mean, the class average is horrible. I know this is probably the worst grade I've ever
He's
gotten.
probably gonna curve it then.
He gave 6 points, but that's not going to do anything to help me because I got an 18 on it. Really, really bad.
Okay, no worries. We'll do our best. It's not that bad. So did it involve first law, and then like what
So
was it?
it was PBNRT stuff.
Okay, PVRT. Yes, yeah.
Yeah, and
You're
then
gonna do a lot of
it's
that, yeah.
saying pressure, asking for root mean square speed,
Okay, I know that one too. Okay,
total
RMS.
kinetic energy. So that was 2. So that was 1 and 2. And then 3 was saying, oh, assuming that 2 gases obey the ideal gas law,
Yeah.
which are moving quicker, and higher collisions, pressure, and kinetic energy lower. So which containers the average kinetic energy of the particles lower, and it's
It's a
like 2,
qualitative. Okay.
yeah, 2 gases, helium and hydrogen. And then
Okay.
the fourth question is assuming a gas behaves ideally, calculate the molar mass of the gas
Okay.
if the density is, and they
We
give
can
you
do that one. Yeah. These
and
questions seem
pressure.
familiar. Yeah. It's just messing with PVNRT and then other stuff.
Yeah, and
First
then
law.
van der Waals equation is given, and then basically asks what, like, he has 2 variables missing, and what are those and their effects on pressure.
Okay.
If Z of a gas is larger than 1 at a
Okay.
certain condition, what is the factor that's responsible? So that was, there's 12 questions total. So then that was the first 5. So I'm just
Okay.
gonna tell you the rest of them. So
Okay.
6 is using van der Waals equation. What has the larger, and he called it an A value, and that's just from the van der Waals equation and like the unknown exponent
Yep.
or
Yep.
unknown variable.
Yeah.
And then number 7 is a gas obeys the equation of state, PV equals RT plus alpha P, where alpha is a constant.
Okay.
Calculate the work. If it's heated at constant pressure with a change in temperature, and then calculate the work. If the gas is expanded isothermically and reversibly.
Yep. Okay.
So number 8 is suppose a system expanded isothermically by an internal chemical reaction at a constant pressure.
Yeah.
And then 2 different gases react to form 1 mole of a third gas and 3 moles of a fourth one.
Yeah, you can do
So
that one. Yeah. Okay.
change in volume, calculate QW and delta RU.
Yeah.
Number 9 is consider compression process of an ideal gas from 10 liters at 1.5 bars to 1.5 liters at 10 bars and 300 Kelvin. And
Okay.
then calculate the work when it's carried out reversibly or irreversibly in one step.
Yep. Okay.
Number 10 is constant volume with a complete combustion of 5.5 grams of this certain substance, maleic anhydride. 77 and
Question. Okay.
yeah,
Okay.
77.9 kilojoules of heat were involved at a certain temperature. What's delta RU? And
Okay.
then the second part is what would delta RH at 298 Kelvin in 1 bar for this reaction be in joules per mole? 11 is calculate delta RH for a reaction from the following enthalpy of formation data.
Okay.
They give 4 gases, or actually a bunch of gases. And then
Okay.
the last question is list the heat, work, and use system involved, greater than, less than, or equal to 0 in a reversible isothermal compression process and a reversible adiabatic expansion of an ideal gas. And that's what was on the first test.
Okay, that's fine. Yeah, take a picture of like all the problems, and then did he already give you a solution for these, or?
I believe so, yes. And
Okay.
I have Gmail up right now. I can send that to you right now.
Okay. Yeah, I think that'll be good. Yeah, if you can send me, because I could just work them out. But then let's talk about what I'm gonna do is let's talk about the ones that you know what I mean, like the ones that we should focus on for the final. Hoping you can get those and then other concepts ready.
Okay.
It's not that bad. It's just probably the time, right? Because there's 12 questions.
Yeah, I mean, he gives, I think, from 3 to like 7 or something. It gives like 3 or 4 hours to do it.
Oh,
So
that's
it's
not
not
bad.
too bad. Yeah.
Yeah, it's just maybe just the amount of like problems that kind of cover all of those. I mean, did you feel like you probably studied enough? What do you think?
I don't think I studied enough, and it's mainly because a lot of those problems were empty and I just couldn't complete them
Okay,
and
yeah.
understand
So
stuff.
and then like I guess the other thing is that so are these problems after take a look at it I can just assess it. But like right now, are they similar to like the T homeworks, like all the homeworks from the book, or not? Similar in sense like is it the same concept or is it like totally like different?
For what I can see, it seems like it is. It's just
Okay.
I didn't really know. I got out early because I just couldn't finish it and I couldn't understand the stuff. And even
Okay.
after leaving, I didn't have any like second thoughts or anything. So
Okay.
I was just lost on it.
Okay. Yeah, I think the in thermodynamics, if you understand like the ideal gas law, first law, it doesn't really build, but then you're gonna see it again, is what I'm saying in the final.
Yeah. Yeah,
And then
definitely.
so yeah, let's try to because I do like doing those problems. The whatever you just you mentioned in the exam, those sound familiar. We can definitely there's solution procedures to get those done, and then just knowing like what those category of problems are that could show up, and then having the confidence like okay, I know what these are, and then I can definitely do them. And then the hardest part is probably like the qualitative stuff, but for the quantitative stuff, we can definitely have like a solution procedure.
Mm-hmm. And he gave a couple equations, but that was it. There's a couple he gave.
Okay. Yeah, I think it's good to really, you know, I'll know more once we go through like each one of those and before the exam, and see like, okay, we should work more on, you know, that, you know, the van der Waal equation, the PV equals nRT equation, whatever, you know those are problems that can change, because sometimes like the example from like the homeworks, yeah, it's pretty straightforward, but then how else can it change, you know?
Right.
Yeah, and that maybe he's gonna show that in the exam. It's always good to like ask those questions while you're studying.
Yeah.
Okay, that's good. Yeah, let's take a look at that later on. But for this one, yeah, just going back to this, does these two kind of make sense? Like why this one is like the second law, and then this one itself is the first law.
I mean, I don't really know, but I do know that
Okay,
what
because
you were mentioning, the first law just tells you like the heat or the work
work,
being
heat,
done
and
or
energy.
whatever, but it
Yeah.
doesn't give you any information on where it goes or.
Yes. Yeah. Qualitative right now. That's a good thing to understand. And then that when you have like a change of temperature, that's like the direction, right? Change of temperature.
Yeah.
That's when you know that's second law, because change of like something is but then for conservation of energy is like every time it says energy, it can't be second law. There is no energy except for like gives free energy. There's no energy in the second law. It's just first law.
Mm-hmm.
So yeah, that kind of defaults it. Like if someone were to ask you, okay, if they give you this equation, delta U is an energy equation. So you can't say that's second because it's an energy. The only time it's kind of like either like is it like first law, second law is when temperature is involved, because you have heat, right? You have heat in the first law, but this is just calculating heat, not the change in heat.
Yeah.
Yeah. Okay. And then is this process spontaneous, or from what we talked about?
Spontaneous is. Let's see. Spontaneous is delta S is greater than or equal to 0.
Yeah, I think it is, right? So
Delta
delta
S.
system. Let's see this one. So delta H over T, and delta of surroundings is delta H and T of the surroundings, right?
Yeah, I think so.
Yeah, and then the process itself that we talked about, like going from hot to cold, it's gonna be this guy, right? In order for that to happen, you have to have delta S is greater than 0. Because if delta S is less than 0, then it's gonna go from cold to hot, which doesn't happen. Yeah. So
I
cold to hot is like it never happens, because delta S can never be. It doesn't.
Yeah.
Yeah. But if T hot to T cold, this is when delta S is greater than or equal to 0. And this is also spontaneous. This delta S greater than or equal to 0. That's the definition of spontaneous. So they're all equivalent. Like when you're saying delta S is greater than 0, T hot is going to T cold. This is equal to saying this is spontaneous.
Okay.
That's just you gotta know those equivalent relations. Like when it says delta S is greater than 0, that T hot is going to T cold, which also means it's spontaneous, right?
Yeah.
And then this right here, like let's see, so delta S, because like what is delta S? Delta S is just delta H, enthalpy over temperature, right?
Delta S is delta H over T.
Yeah, where this is enthalpy. And then so from that equation, there is a way for you to prove this as well. Like, is it delta S is greater than 0? From that from the delta surrounding delta H over T of the surroundings. Of the system. I think this is delta H of the surroundings. You can also use this equation to prove that delta S is greater than or equal to 0. But like, I think that the easiest way not to work with equations is just to think about it this way. You know, think about it like if delta S is greater than or equal to 0, in reality, you know, things that are hot open to the system, the surroundings. The system is open to the surroundings. The hot things will always go to cold thing, the colder temperatures, and that process is spontaneous. It's natural.
Mm-hmm.
Yeah, I usually just think about it that way instead of like the actual delta H over T. It's always good to think about it that way too as well. Okay, I like these questions, the 7 and 8. What is the difference or the relationship between equilibrium and reverse process?
Well, I mean, so if something is reversible, then it should be in equilibrium, right?
Yeah, that's the relationship. Just to expand on that, like we call a process that can be reversed. Like this is what I said. Can be reversed if you know you have a small change in thermodynamic state. Reversible. It can be seen that there. And how you say this is like if a process is reversible, then you've probably seen this by definition. It must pass continuously from one equilibrium state to another. You've seen that before, right? Or heard of it? Like if a process is reversible, the system must pass continuously from one equilibrium state to another. That's how. And then when it's reversible, it follows the same process, the pathway. That's why it's in equilibrium. If it's irreversible, it follows like a different process. Let's talk about that one actually, if it's irreversible. So irreversible, the meaning of irreversible is it must take a different path. It must take a different path to get back to its original state, right? That's irreversible. So a spontaneous process is what reversed only by taking a different path. It's pretty much like the same thing. Like a spontaneous process is another way of saying an irreversible process.
Okay.
So, but you're taking a different path. An equilibrium process is taking the same path, which is what a reverse process is. It's taking the same path to get you back to the original state. So like, just to, you know, if you were to memorize like what these mean, like this is pretty much the same as a reverse. And this is pretty much the same as like same process or same pathway. Same pathway from state to state. Same pathway through states. And then for spontaneous pretty much means irreversible. And then this is pretty much saying different pathway through states. So these words are all synonymous, equilibrium, reverse, and same. Spontaneous, irreversible, and different pathway. So like, yeah, that's just pretty much like, okay, do you know what these mean? But there is a relationship between those. Does your professor ask you guys these? I haven't seen the exam yet, but like, is there one like this where like, okay, what is this process? Explain.
Let me see.
It seems like not like a midterm question though.
Yeah, I mean, it says like on one of them, it's like based on the van der Waals equation for each pair of particles, which is expected to have the larger a value, and briefly
Yeah,
explain
that
why.
one, yeah. Yep, yeah. So in order for you to answer those questions, it's always good to hash out like, you know, the factors that will affect, like, you know, like in the equations of or whatever equation it may be,
Mhm.
know how the different factors of that equation that come into play, either like changing or increasing that value or decreasing that value, how do they affect overall the you know the equal how does it affect the actual equation? Like for example, the van der Waal equation, or like PV equals nRT, the ideal gas law. If you increase like temperature, if you decrease volume, how does this affect pressure? Stuff like that. Same with this one. Like, you know, for the Gibbs equation, or let's not even go back to that. Let's just go to this guy. Like, if you have like an increasing temperature for the system, or decreasing temperature for the surroundings, what does that mean to your entropy? It's the same question, right? It's like along the same lines. Like, there's no number, but knowing the different relations will give you kind of like a better sense,
Mm.
kind of like a real world aspect. Because like, at least you know, the if you were to like if you were to like think about, oh, should you do something, it should be always be informed by the equation, and that can be like many things. But
Okay.
yeah, let's talk about what number is this one? 9 and 10. Let me take a look at this one. I think this one, maybe I'll just show it to you. It's just a bunch of math that you have to like derive some things.
Okay.
But so they want you to get this information. They want you to prove that delta H of surroundings, the enthalpy, is the same as delta Q of the surroundings. And how I would do that is like pretty much from this equation: H equals the internal energy plus PV, and just take the derivative of that, like a differential, whatever. And then you're gonna see that this is a P and V are constant, and when you take a derivative of that, it's gonna be 0. So then that right there, it pops out. This is pretty much the same as this guy. And then it also asks you to prove a few things. What was that one? I think it was like getting a relationship for delta S total, delta S system, and delta S surroundings. So like how I would do that is just start out with Q and then the delta H. It's, yeah, like I'll just try to like follow these equations, and let me know if the something seems unclear like later on. And then it just pretty much tells you, you know, do these things, and then prove this equation, and then yep, yeah, like this is how I would do it. Just see later after, you know, like showing this to you right now is I don't think it's that much worth it, because then it's like, oh, okay, where did you get like, but it's pretty much like applying the enthalpy equation and then the entropy, and it's like taking the derivative of them and then kind of like putting them like together so that you can get the final equation that they want you to prove, if that makes sense. That's for 9 and 10.
Okay.
It's not that bad. It's just let me know if there's something in there after you take a look at it. Right now it's probably like, oh, okay, but like, yeah, let me know if there's something there that doesn't seem clear. Okay, number 11. Let's take a look at number 11. What is the total entropy for a reversible and irreversible process? So for A, it's like reversible, and B is going to be irreversible. The way I take a look at these is, if you have, there's like you know, a large long explanation, but like at the end of that, a reversible process is pretty much when delta S total equals 0, and an irreversible process is when this is greater than 0. That's just like something to take in. But that's what it is. And let's see this other one. This one I can probably, this one seems to make more sense. Number 12. What is this one asking?
Well, it's just saying using the first law of thermodynamics and then derive these equations.
Okay, so this one isn't that bad. Let me try to explain this one. So if you remember this equation, U equals Q plus W, right? That's just eternal energy. Or this is like heat absorbed or release. This is just pretty much change of heat. And then heat, and then this one, what is this one? This is work, right?
Yeah, it is.
Yep. And then so that right there is what? This is what is U?
Energy?
Yeah, this is the energy, internal energy. So that this is your first, like in essence, like energy, heat, and work. So when you take the first law, take the derivative of that, you get delta Q of the heat and delta W. And then so what is delta W, which is the change of work? It's just going to be this guy. I think this is in one of the equations that you can use when you have like I have to take a look at like this equation, but this is what usually happens. Like delta W is minus P, because you need this, you need to prove something with this guy, which is the pressure of the external times the change in volume. And then if you take a look at this guy, the change in heat, we know something about this change in heat, right? Like we have an equation for this. I think it's like in the previous page. Let's look at this one. Yeah, in the previous page, if you take a look at number 1, for a reversible process, you have this equation, right? The delta S equals delta Q reverse over T.
I don't know where it is on page 1.
It's on you know where page not it's like 2 pages before that guy. So like after you have 11 and then there's 9 and 10. I think it's on 109. I think that's 109, page 109.
Okay.
It says model 2.
Yes.
Okay. Do you see this equation? This one right here, this one. It should be number 1.
Wait, which equation are you pointing at? Or
This one right here. The delta S equals delta Q over T.
okay.
Do you see it?
Yeah, I do.
Okay. So that's the equation. That's the change in entropy equals the
Entropy.
change in heat over temperature. Change in heat is pretty much H. So this is the same equation. H over T, entropy over T, delta Q reverse over T. And then you just times the temperature over, and then you should get something like this, right? You should get something like this.
Mm-hmm.
And then that's what we want. So what I would do is, so you have delta Q now, and then you have delta W. You put it in the differential form of your first law. And then, so you have delta U, same delta U, the delta Q, which is this guy, TDS, temperature times the change in entropy. And then delta W, we got that as this guy, right? Minus PV, or PdV.
So how are you able to tack on the PdV to this?
What do you mean, like the delta W?
So is delta W equal to negative PEX dV?
Yeah, external pressure times the change in volume. External pressure change in volume, because like the change in work, you've probably seen this before. It's just the PdV, but then it's like it's negative.
Why is it negative?
Okay, so that part, let me see, work done, but it's because of this guy, work done by or work done on. It's something about that one. I think it's like work done on is. Let me just is negative PD. Do you remember talking about work done on and work done by? There's a difference between those two.
Work done by.
Yeah, and one of them is negative, right? Work.
I don't know.
So let me let's brush on. Let's talk about that a little bit. Let's see. That's from first law. It's like I don't know if you guys covered that, because if you talk about altogether, it's just this guy. Let me see if I can FDS PdV. It's pretty much just like if I can. And when you have this guy, remember if you have this, and when you have like this,
I don't know. I don't know what the FDS is.
this is your work, force at a distance. Force done at a distance is work, right?
Why is distance ds? Or
That's just how I usually look at it, because like you have a force done at a distance, which is ds. When you're pushing something, right? you're pushing this guy. It's gonna move, right? A ds. That's just definition of work.
uh-huh.
I can cover that more. Like
I
if
mean,
you
I
want.
know force times displacement. I just didn't know it was okay. Yeah, maybe I'm just thinking it's like FDX.
Yep. Yeah. So you know how like when you have this guy and then you have this as like delta S, when you're pushing something and then it moves, that's the distance or displacement. I mean, it's not really displacement, because you can say it's being. I usually associate displacement by like stress, like inside internal displacement. And delta S is like a movement, like a distance. In essence, that's how I usually say it. Because then I usually associate a display. You can display when you're saying something is being displaced. That is just moving it at a distance, and then work by definition is like force done at an object that's that moves it at a distance. So that's gonna be if you derive that. I don't want to go off on a tangent. It's just gonna be P dV, and then the reason why it's either minus P dV, it's either plus or minus P dV. If it's plus, it's gonna be work done by or work done, and minus if it's work done on.
Could you repeat that? I'm
Uh,
not understanding the PdV.
okay, so the work is after you do this, this derivation, force at a distance, you're gonna get PdV. But then work has a sign, right? It's either positive work or negative work, right?
Wait, is force the PdV or is the distance the PdV?
No, it's all the same. It's all the same. Like that's what it is. Like work is PdV, but at the same time, it's also this guy.
Okay, what is P and what is dV here?
P is your pressure. dV is your volume. From the PV inequality, it should be the same. Is what I'm saying. Here, I'll show you something. This is what I usually show, work and energy. Did your professor show you guys how to derive the work equation? I'm pretty sure you guys done this one.
Maybe.
Because, yeah. It's the main question that people usually ask, like, what is the sign of work? Oh, okay, I see, I see. Okay, I'll show you that later. I think it'll be better if we talk about that. But right now, just think about like this positive is when work is done, it's gonna be like done by, it'll be this guy. And then work done done on, it's gonna be negative work. I'll explain this later, like if it's because this one we have to like really talk about the first law, and then if you want to if you want to see how this is derived, I can show you that later as well. This guy,
Which one?
this W, Y is a FDS and then PDV. But right now, double like work is just PDV, and then this is negative because it's work done on. So if you take that work done on, then you could just plug it in here, and that's how you would get like the equation that they're looking for. Does that kind of make sense, or not? That like how you would just plug that in and then get this equation.
No.
Okay. So delta Q, do you get that part at least?
Delta Q, that would be, I don't know the equation for dq.
That one is in page 109. That's just the entropy equation.
Entropy equation.
In
There's
109.
ds equals dq over t.
Yeah. And then you just transfer it over because you dq equals TD, the temperature times the entropy change. TDS.
Q t equals ds, so then This makes dq equal to ds times t. Okay, then this would be
The
okay.
only
So
thing that's different there, like, is this guy. So it doesn't. I don't think this shows you, because this part here is where the second law is, right? The TDS. This is like technically first law because you have this work here. So once you have this as positive or negative, then you can finally apply this equation. And after you apply it, you just move things around. This is what it wants you to do. This is the first equation. If you take a look at it, delta U equals TDS minus P external pressure times the dV, right? That's the first thing that you have to prove.
I don't know.
And it's all from the first law. Like when you take the differential of the first law, that's how you're gonna get this delta U, right? And then now you have to only find delta Q and delta W. And that's what that's what you have to figure out.
I don't know. There's just, so I know that you can substitute TDS for DQ.
Yep.
And so this just be DQ minus DW?
Yeah, well, DW can be positive or negative. It depends if it's work done by or done on. For this equation, I think
Just
it's
be plus.
yeah. For this equation, I think it's work done on, because then it's negative. So if you take a look at that second equation on number 12.
Okay, and I mean, on these, are we just finding the simplified versions?
Yeah. So like when you take a look at this guy, when you transfer it, let me just explain this part. So you know how like you divide this by t, right? After you divide it by t, this guy goes this way, right? And it becomes plus. And then you're trying to isolate ds. So this is ds. So now it's plus, but initially it was negative. So that's why you can say like, oh, it's negative. So if it's negative, then that must be work done on. So if this is plus, then this will be negative, which it doesn't really explain and tell you like, oh, which one should you assume? So I would just say like, okay, they probably assume that this initially is negative because you needed this to be plus in the end. It's like one of those things like, okay, you have an equation, and then how can you, what do you have to assume? Because delta Q, it doesn't matter what you assume. It's not like positive or negative. It's TDS. You already have that one. But this delta W can be positive or negative. But since this gives it to you, the ending is plus, you can always work backwards, right?
I don't know. I'm lost. DF equals the du over t.
Okay. It's
So
not, like I said, like, do you understand at least this delta Q equation?
delta q over t equals ds.
Yep. But then delta Q is also in the first law, right? This equation. And then this delta U equals delta Q plus delta W. Delta Q is in that equation, the one that you're talking about, delta S over delta Q over T. The one thing that you need to know is delta W. This right here is by definition, this is delta W.
What is?
This P, this term right here comes from delta W. This right here, this DS and T. Because we have to do some some math here to actually isolate DS. This comes from delta Q. Delta Q, that one isn't that hard. But what I'm saying is like delta W gives you this P dV term.
Okay, which delta S are you talking about?
This guy. This guy. Here, let me just try to like explain it to you. It's so you have delta Q, right?
Okay.
Maybe it's easier to look at this. So
No,
delta
it's
Q.
just because it's hard to see exactly what you're circling or what you're referring to with I guess
Okay.
things are being done on the
So
computer.
so you know how like let's just talk about it like simply. So U equals Q plus W, right?
Okay.
And then you take the differential of this guy. So differential equals differential of Q, right? You just like, I mean, this is just the definition of like doing that. And then, so what is delta Q and what is delta W? You know that delta S equals delta Q over T. So you just move things around, right? You just move things around. It could be T here or whatever you want, T, ds, dq. So this is delta Q right here. This is pretty much the same, right? And then now what is delta W? We know that work is force done at a distance,
Mhm.
right? We know that one.
Yeah.
And then like I said, that this delta W is this P dV. Is this positive or negative? This positive or negative, if it's positive, is work done by. And then negative is done on. But like, so why don't we just test it? Like I would say, why don't we just test it for positive P ex dV and dW equals negative P ex dV, right? I mean, that's how I would do it.
Q, T. So this is saying du, but our equation is just u. U
Which
equals
one?
dq plus. So like the ds equals du over t. Um, our one of the equations we have is u equals dq plus dw.
Yeah, and then du is dq plus dw. Yes, yeah, that's what we're trying to look for.
So it's not just u equals dq plus dw, but it's du.
Yeah, it's du. That's how you. If you look at this equation, there is du in here, right? I'm talking about the equation on number 12, 12a.
Yeah, I know. I'm looking at the two equations they're giving you.
Yeah, it says du. There's du in there. So that's why you have to take a differential of your first law and then distribute that. You know, you have du equals dq plus dw.
dq plus dw.
Yeah, and that's
Okay.
how you. That's like the first step. Yeah, okay, because that's like the sane step. You know, it just makes sense to do it because there is no u in here. It's like du. So you need to get du. So you just, why don't we just take the differential and then map it through like the equation. And so that's how, in my mind, I'm like, okay, I need to get dq because it's in there. And then where can I get dq? That's like my first question. It's like, oh, I can get that from this entropy equation. So, which is just right here, right? You got that. That one's easy. But what about dw, which is the distance, the work, the force done at the distance?
Let's du. So du is that. So you would have du times t minus dq.
Yeah, it would. What I would do first is no, kind of like check if it's positive or negative, and then you could probably go because it doesn't indicate which one. Like when you're doing you could check if it's positive by just plugging that in. Like you can just say, what if we had like du, right? And then let's plug in what we have, TDS. And then plug in P positive P dx dv, right? Like that's our first case. And then Let's take a look at like what equation we have to derive. But it doesn't want you to do that. It wants you to do this negative because the first equation tells you it's positive. It's negative, isn't it? It tells you it's negative, I think. Like this guy is negative. It's not positive. So I will throw out the work done by. So I would probably throw this guy out. Does that make sense? I mean, like, it's just looking at that equation. Which one would you choose?
I mean, dW doesn't include the time in there. It's just PEX dV. There's no.
Yeah. That's the definition. Here, let me. It's definition of work. It's like work. Because once you derive it, you're gonna get the V. Okay. And like the way that you probably think about work is because work can be this guy. You said time, right? You said. This is like
FV dt.
For a gas, this is how you usually do it. Like it's PdV. This is the gas B of A. There is work done by a spring which is this guy, and it's also done by like a gas, which is the PdV.
PdV. Okay. I don't know what the F times V dt means. Because I thought it was just F dt. I don't know where the V would be.
So V, okay. It is deep.
Velocity?
Yeah. But then this is dot, though. This is dotted.
Okay.
As I said, like I'll derive this. I'll give you my derivation of this next time. But the gas version of this is this guy, and this is what we're using. This is usually like for like a mechanical system, spring, mechanical. But for gas, it's this pressure, and then dV, volume. You know this one. PV equals from PV,
Yeah.
And that's work. That's work in chemical terms. I don't know if your professor talked about that, but work in chemical terms is like PdV. That there's like this derivation for that makes this like work where you derive it from this guy.
I have no idea.
I'll show you that like a full derivation because I thought you guys talked about it. What did your professor talk about work? What does work equal?
Let's see again. Work T1.
Yeah. Let's see if I can see what there was a derivation in one of my notes that maybe I can just pop that over and explain using that one here while you look for that.
Okay, I mean, there's a work is equal to dW.
Work equals to dW?
Yeah, from initial position, final position, dW.
Okay, yeah, that's just change of work. That's just change of work. So let's see. Maybe I can, let me just open up some of these slides. Because now we're talking about the gas. Like this.
I mean, work equals force times distance.
We know that one. That's like the mechanical, like spring, force times like distance, displacement. But then
So
in terms of gas, though,
force over area equals external pressure. F over A equals PX. That's it.
Where's this one? So entropy. Okay. I would probably just memorize that though. Like that W is also for a gas. It's just PdV. It's just one of those things. For if you're talking about like a force, it'll be force at a distance. Yeah. Here you go. Force. And this work energy. Okay. Okay. Because you know how like you have work and then kinetic energy, change of kinetic. You also have work. You can derive the potential energy, right? With work. This force. Do you remember that one? That probably is more familiar, right? The relationship between potential energy and work, and then kinetic energy and work. That equation comes from this guy. But then, what about for a gas? Let me see if I can show you. Like,
I don't know. I can't remember the potential energy and work and kinetic energy and work.
so you forgot how to do that with this guy? Okay. Let me share my other screen, not this screen. Stop sharing. Let me just show. Maybe yeah. It will be helpful if we go through that process. Okay. Let me know if you see my screen.
Okay.
Okay. Let's just go over that. You said the potential energy and kinetic, right? Like from the force displacement or force done at a distance. So this is just basic stuff that we talked about, but like I think it's relatable. Let me just go back to what does this mean? So like I guess this is the formal definition of work, right? Form of energy in transit resulting from a force acting through a distance. This is this guy, right?
Mm-hmm.
Okay, so we all know that, and then that force done at a distance in transit. So now let's talk about what does that mean in terms of energy, like change in energy. So what if you had like this guy? So let's talk about force. Force has a direction, right? Force done at like a horizontal position. This is what this means. And then this dx is like a displacement or like a movement distance. And then once these are just how far the distance between first point, second point. So after you do this, right, this force using like Newton's law, right, or force dv, vdv. After that, you do this derivation, this integral, you get this, and then this is a change, right, in kinetic. So that's just using the mechanical version of this guy. So now that's kinetic. Well, what about potential? So potential, that's things that are, there's a height elevation there, right? There's a height elevation. So let's not take force at like a horizontal, but a displacement between like, in the z direction. So what does that mean for force? Force now isn't just, it's not md or mvdv or ma. It's mg, right? Force here would be mg because it's a falling object, okay, or at like an elevation. So once you do that, then it's the same concept. You're still causing work to happen because a falling object is, what's the force there? It's the weight. And then what's the distance? When it changes, from point A to point B, or point 1 to point 2. You do the integral. After that, you get the z. This looks familiar, right? Like mg times z2 and z1 delta z. And that's just potential. I think those ones come from.
I guess I'll write that down.
Okay. Yeah.
I don't know.
Okay. Yeah. Like that's coming from the force at a distance. That's work a mechanical type of work. I can probably send the slide to you. I think it'll be better. I'll send this, like the slides. Yeah, it'll make more of I mean, like I think these notes are quite nice to have. Okay, let's take a look at when you apply thermodynamics now. So that wasn't thermodynamics. That was just work and energy. Thermodynamic definition of work. It's the same, but it's slightly different. So if you take a look there, what is the thermodynamic definition of work? Work is done by a system on its surroundings. We talked about that, right? Like what the system and its surroundings. So you have the system in this one can, you have this boundary. It's a system, and everything outside it is your surroundings. And let's see what it says. If the sole effect on everything external to the system could have been the raising of a weight. I wouldn't focus on that more. It's more just like work done on a system. You're still doing work on whatever system you're gonna have this boundary in, and this on its surroundings. So that's a thermodynamic definition of work. The other one was just force and distance. That's not thermodynamic. Now when you apply the system and surrounding, this is thermodynamics. So this is what I was talking about. This guy. If you take a look at work, that's positive work, right?
Right.
Done by the system. So work done by is positive work.
Mm-hmm.
Or work out. Yeah, and it's like work out. I guess it's being yeah. And then work in is negative work.
Mm-hmm.
Work done on the system. So this is what I was talking about. This doesn't really define the thermodynamic definition in terms of like PdV. It doesn't define it yet. We'll get to that. But positive work is plus, negative work is negative, is minus, less than 0. And then these ones didn't really tell you, so that's why maybe we can just assume 1 and then kind of like derive that equation. Okay, let's take a look at this one. Isn't that important? This one's not that important. Here you go. I think this is where it starts talking about these guys. So this is like the thermodynamic version. This is how you relate these two things: the mechanical FdX. So you have that integral here, right? Before the W equals this integral.
Yeah.
And you take the differential W, which is what we're trying to do in our problem. That integral gets canceled out by the derivative. So you have FdX equals delta W. And what is F?
Hmm.
Do you remember what F is? It's
MA?
Yeah, in Newton, but like it's just it's a stress times area, right?
I didn't know that.
Yeah, force is stress times area. Yeah. And then I guess let me make that related, because stress is more, it's not thermal, you can't really apply it here. What is stress in fluids? Pressure, right?
Okay, pressure.
Yeah, it's the same thing. PSI, pressure, PSI, stress is PSI, but that's in solids. So since we know that, like, force is like pressure times area, right? We know that one, right? Pressure times area.
Okay.
Then this area times dx is dv, right? And then this pressure, I don't know why they changed this to a small p.
PdV. So pressure times area is just pressure?
Pressure times area is force. But then area times dx is dv. Like pressure times area is force from our usual definition of work.
Okay.
But force is pressure times area. And then you just take this pressure out, and then this area times like differential, like x whatever is a differential volume. And that's pretty much the definition. Like dv equals pdv, and if you want to use the differential form, it's this guy, or like the integral form, it's this guy.
Okay.
So wait, your professor didn't talk about this one?
I don't think so.
This is like, yeah, okay, that's fine. It's this is the, like, if you were to talk about work in terms of thermodynamics, this is the work in thermodynamics, because we have to work with gases, chemicals, so it has to be related to what is the usual equation for chemicals? Ideal gas law, right?
I guess.
And then how can we work with forces? You know, like we can't really work forces in like in chemicals. So that's why we have to take what we already know, force down a distance, and then relate that to a gas or chemicals, and get like a PDV, which is related to a chemical or like gas, whatever. Okay, so that's the definition that I guess the long ways of getting there, but this delta W equals PDV. Okay. I guess going back to this thing. Does that kind of like make sense? I know it's a little long, but like that's how you derive that one.
I'm just lost. I don't know.
So this is that equation, right?
Okay.
And delta W equals PDV, either plus or minus. Okay, so let me see. After all of that, like, so after all of that, we can say that this delta W is negative PDV, and you just plug that in. In this case, I kind of hopefully explained that it is PDV, but then what is the sign? Is it positive or negative? On this one, they wanted it to be negative. Negative. They didn't tell you, but that's how you have to assume it for the equation.
I don't get it. I am completely lost. I don't know
Okay.
why.
What part? What part? What part?
Okay. I guess from the beginning, I guess I just think you were maybe going too fast.
Okay. Okay. What part did you wanna on this problem? Is it on this problem?
I guess just the second equation, that ds equals du over t plus pex dv over t.
The second equation. This equation.
Which one?
Sorry, this one is like. Which equation? This one or this one?
It's the second one.
This guy. This guy.
Yeah, the ds. Yeah.
Okay. Let's talk about. So do you understand this guy though first?
Yeah, I understand how to derive everything. How you can get to du equals dq plus dv, but it's just the second one that I don't get.
Okay. So let me write this and see how we can get to this guy. Right? So
Okay.
let's try to. I can just like remember it. Okay, let me just go over here. So what was that equation?
It's ds equals
Okay.
du over t plus pex times dv over t.
Okay. Let me see. Plus?
Yeah, plus pex dv over t.
Okay, that's what we're trying to derive. Okay. So let's go to the first one. Du equals TDS minus PEX times DV. Let's take a look at this guy, dV. So this one, how do we get to this point, right? Is that what you wanted to know?
What do you mean? The T, because like I know how to find the first equation, how to derive that first equation, the TdS minus PEX dV, but I don't know how to get the ds equals du over t plus PEX dV over t.
Okay, so how do you get from this first equation to the second one, right? That's the question.
No.
Okay, so what do you want to know?
No, it says the problem itself is asking to derive each individual equation, not to convert one equation to the other. Like,
Yeah, but the thing, you have to use this equation to get the other. It's not like this is isolated. This is not isolated. This equation is used to get this guy. It's not like this just came from nowhere because this is PEX is the same PX, right?
yeah, I mean, you would just multiply the t over to the other side to get the TdS equals du.
Exactly, yeah. That's what I would do.
And then you would bring the other, you would subtract the PEX dV and bring it to the other side.
Yeah, that going from this guy to this guy is really just math. The hardest part is this guy. The hardest part is this guy.
Okay, I just don't know then, because when you kind of talked about like you pulled up the slides, I just didn't understand any of that. But
Okay.
um, if I'm just looking at just converting this first one to the second one,
Okay.
how would you deal with the second t?
The second T.
Yeah, the PEX times dV over t.
This guy.
Yeah, where would that one go? Because I know there's one on the t. Because
Okay, okay.
I mean, you would pull out the t, so you would just have a 1 over t times the du plus PEX dV.
It would be like obvious. So you have du, right, on this guy, right? And then you plus this guy, right? You plus this guy on the other side, right? You have this guy right here.
Well,
And then you divide. What are you trying to get here?
um,
It's really just the math. It's just isolating the ds.
so before you brought over the du over t and the PX dV over
Yep.
t, could you just pull out the denominator? So you would just have a ds equals 1 over t times,
Oh, you mean this
in
guy? You mean this
parentheses.
guy right here? Yeah, yeah. It's just it's the same denominator. It's the
Okay.
same guy. It's the same variable. Here, it's pretty much this guy right here. Or you could have done that. Whoa, what happened? Okay. Right?
Okay. Let's see. So TDS.
But yeah, like I said, like all these like derivations. Did you guys have to do any derivations on the exam? Okay.
I'm just checking.
It's not bad. It's just a lot of I mean, it's like preliminary steps. Learning how to derive seems like okay, that's how you understand it, but using it, that's more of like a test problem.
I don't see any derivations on here. There might have been, I just don't see it. I mean, there is, yeah. On the first one, for ideal gas, use PV equals 2/3 NKE and KE equals 1/2 NAM VMS.
Okay.
Derive VMS
Yeah.
equals 3 RT over M to the 1/2.
Yeah. As I said, like if the like most of the stuff like in deriving things, it's more of like just combining the equations, and you really need to know the definitions, you know, like, especially like that dw, the work, like just knowing the different what is ds, what is dq, what is h, what, you know, and then like kind of like stepping back. It's like, oh, what can I do with that? Can I take a derivative? What is constant, like what we just talked about in like the other equation, where like pv is like constant, it goes to 0. We can do more of these ones, but does this kind of like make sense now more than, but then we could talk about it again if it doesn't, but does it make more sense in how you derive it?
Yeah, I didn't know that it was you had to derive one before the other. I thought these were two different things, and you would have to use the different equation.
Yeah, it's that right there is probably like something maybe you could ask your professor. uh, as far as I know, it seems like it's gonna be, it's not like, it's, what is it saying, starting with the first law, right? We did that, expressed in terms of dq and dw, we did that. Use model 2 to derive the following expressions. I mean, I'm thinking that doesn't tell you to say they're separate. It just tells you derive the expressions.
Yeah.
Okay. Yeah, it's the like the concept kind of fall into it. I mean, if you take a look at this equation, you know, like this is the main equation, right? You have this entropy, the internal energy, and then PV, which is work, right? PdV. So, I mean, just looking at this equation is kind of like drive the concept, is what I'm saying. Okay, I think that was probably the last problem of this guy, but I think the B, let's look at what B is asking. This one is really like applying that equation and the ideal gas law. Let me ask, how would you attack this one?
I mean, you could make two copies of the first one, the du equals tds minus pex dv, and put a lower temperature for one and then a higher temperature for the other.
Okay, so temperature of ideal gas law is increased reversibly. Okay, it just says that under condition, there's like keywords in here, like, you know, like because it's saying this is a reversible process, and then it says here constant external pressure, and then mainly it's asking you what is ds, right? What is entropy? It is the like the delta S change, is that 0? Is that positive or negative?
I mean, if you made PEX1,
Yeah,
DS, you don't know really what DS would change to be.
you don't know that one. Yeah.
DU, don't know either what that would become. I don't know.
Okay, so for this one, I guess I'll just kind of like briefly explain it. So they give you reversible conditions, right, as a keyword, and then they also tell you constant pressure, right?
Okay.
Let me just like rushing and doing this thing. Constant pressure. So what does that mean? Constant pressure. That's isobaric, right? If you, do you remember that word? Isobaric.
No.
Okay, it doesn't matter. It's just constant pressure. Does that sound familiar in terms of ideal gas law?
Yes.
Which equation does it simplify to?
So it'd be P equals nRT over V.
Yeah, but like, do you remember Boyle's, Charles, and Avogadro?
Charles, not Boyle's, not. No, I don't.
Yeah, it's like one of like every time like I ask this like ideal gas law, it's like, do you remember? Yeah, there's three guys that like simplified the ideal gas law, and one of them was Charles. And then Charles assumes constant pressure.
Let's see.
Let me see. PV equals nRT. So if you that's ideal gas law. If you move the T to this side, nR over T over P. This is ideal gas law, right? This guy. This is ideal
Yes.
gas. Okay. So we know that in ideal gas law, what are the constants? Just regular constants. We're not assuming anything. R is a constant, right?
Yes.
And N can be shared. Given one, you can get the other, but it's literally just a constant.
Mm-hmm.
But P, V, and T, they're not constants, right?
Yeah.
But if that's like the general ideal gas law, but when we assume constant pressure, that means, you know, obviously it's going to be a constant like nRT. So let's try to look at this. nR over P equals V over T. And when this is constant, this is Charles' law, which is this guy.
Mm-hmm.
So VT is the one that you have to only compare. And then they're equal because nR over P is constant between the two. Okay, so why does that matter? So like, we didn't really change that, but then there's also this definition that if you take a look at it, let me think about this one. du CVT. Okay, well that's what they give you, and then let me just think. Oh, okay. The reason why we talked about that is the constant pressure one is because of like, do you remember in that equation we just derived in part A? Do you remember that one?
Which one?
This equation, this one.
The du.
This is ds. This is ds and this is du. Yeah. ds. This is du. But this is positive though.
Okay, so the second one. Okay, so ds du over t plus dx dv over t.
Yep. So we're gonna have to use that in this case.
Okay.
So the funny thing is like how are you gonna get a conclusion? That's what you have to figure out. So if you think about this one, an increase in temperature, like from Charles' law, an increase in temperature gives you what? An increase in.
I guess well, it would be a decrease in volume.
It would be a decrease in volume, yeah. But like, what about an increase in volume?
Your temperature would have to be lower.
Yeah. And then what about your overall? Because you have to get a conclusion from this term. This term has to go up. If you're given the what it's given you, because you're given constant pressure, okay. Does it give you anything else?
I don't know.
So this one gives you a T. T is not changing. So T isn't changing, so it must be the volume.
Well, how do you know temperature's not changing?
In this equation, it's just T is the same. You know this equation right here? T is the same, but it doesn't give it to you though. What I'm saying is it's not a change. Like only dV is the one that's a change, a dV.
Which equation is T constant?
Let me see. So what I'm saying is this T right here is not a change. It's only this guy, the delta V. So this T can be like constant, you know, it's constant between these two equations, these two terms. But then this dV is a change in temperature.
Is it
Change in volume.
the boxed green one?
Yeah.
Okay. So how is that one the same?
Because given like a temperature, they share a temperature. But then the dV cannot, it has to be like, it has to be related by Charles' law. That's how you relate them, because the pressure is the same.
Yeah, but it says that the temperature of an ideal gas is increased.
Where does it say that? Then if the temperature of the ideal gas is increased reversibly. Okay. So if it's increasing, that must mean your volume is decreasing then.
Okay.
Because if the temperature of the ideal gas is increased reversibly, the volume is decreasing. So
Yeah.
if that decreases, and so this whole thing is decreasing. Okay. Okay, so if you take a look at that, right? Like maybe this guy is decreasing. So that doesn't give us that much information, right? Like to assume what ds is. We can't conclude what ds is yet. So we have to take a look at the other guy. And then I think an equation that you could look is, do you remember this equation? Is that like an equation that you guys, du equals the cv dt?
Oh, the du equals cvdt.
Have you seen that before?
I think so. Yeah.
Okay, good. So that equation is just like heat capacity, constant volume, which is the cv, and then how can we use that one? We have to use that. The reason why we're using that is to get some conclusion on du over t. So du over t, let's take a look at this. If your temperature is increasing, what does that tell you about your du?
Temperatures decrease. Temperatures increasing.
I think this one has to increase too.
Your du would also increase.
Okay. So if this one increases, this one decreases, can you really conclude that it's
what decreases?
This dv? Because remember we talked. I'm just trying to see if the constant pressure will give us an increasing second term or like a decreasing second term. This is a second term. So like if you have this constant pressure, and then your temperature is increasing, does that mean your volume is gonna decrease, right?
Okay, what's your second term?
Second term is this pdv term.
It's the PEX-dV?
Yeah.
Okay, so PEX-dV is our second term. Second
Because
term of what?
of your ds equation.
Of the ds. Okay, yeah, ds.
So the main thing here is, can you conclude, because if the first term is increased and the second term is decreased, it kind of looks like it's going to be zero then, no?
So
Or
it
can you
says,
not determine it?
so the du is increasing with the dt.
For sure, du is increasing because we know that like if the dt is increasing, that's given to us, du has to increase.
Okay, and so then the first term's increasing, and the second term is
If you increase the t, okay.
so dt. So c. Okay, so it's a dpx dv over t. Okay, how do we know that one is decreasing?
This dv over dt, the px dv over dt.
Yeah.
I would think, like right now we're trying to assess if this is actually decreasing, because if your temperature is increasing, right? We know that one. Does it say, is it differential if the temperature of an ideal gas law increase reversibly under constant external pressure? So if your temperature is increasing, actually, if it, let me think. T1, if you assume that it's increasing,
Okay, px dt should decrease.
let me think though, because like you have to think about like Charles' law. V will, because dv right here is v2 minus v1, and then your temperature is increasing, so T2 has to be greater than T1, right? I mean, that's kind of like logically thinking about it.
Mm-hmm.
But then you still have to apply Charles' law. So if you say like V1 over T1, I guess V2, this is going to equal 0 somehow. And then so you're saying that, okay, so you have dV up top over hold up. Obviously, it's just T2. And T2 minus T1 equals 0, okay? And then, so, okay. T2 minus T1 is going to be positive. So how can you conclude that this is decreasing? Let's say PV equals nRT. An increasing temperature at constant pressure, right? This is constant, so this doesn't really affect us. Yeah, if you think about it though, like the PV equals nRT gives us this relationship, right? It doesn't matter what your pressure is, or N or R. There's a relationship between V and T, right?
So what does the V alpha T mean?
It's a relationship. It's like, this is how you write relationship. It's like an alpha. Okay, maybe I'll not talk about that one. This just means like if V goes up, this says that T has to go up, right? And if V goes down, then T has to go down. If it's like V is like 1 over T, then it's the other way around. But it's from the ideal gas law, PV equals nRT. Pressure is constant. So if pressure is constant, if volume increases, or temperature in our case is the given one. If temperature increases, then this implies that the volume increases. So I guess what I did have in the beginning, it does make sense. I was just trying to look at like what the heck's going on. If this one goes up, this one has to go up. Because of the ideal gas law.
Ideal gas law.
PV equals nRT. Pressure is constant, so V and T are directly proportional. So that makes sense then, doesn't it make sense? Like, then there's that. So the first term du is from the reversible condition, from the constant volume heat capacity. The second term is from ideal gas law. Increasing temperature equates to increasing volume. Because your pressure can't change. Your pressure can't change because it's constant, then that must mean your volume has to go up. I know it's just a bunch of those like factors that like if this goes up, this goes down,
Yeah, I get that the V1 over T1 equals V2 over T2. I know that relationship, but I don't know how that applies here with the PV equals nRT.
Okay, so at the bottom here, hold up. So like this PV and RT, maybe this one doesn't like apply. It has to apply because it's Charles' law. But then the main thing to look at is the ideal gas law, because this is Charles' law comes from the ideal gas law, right? Charles' law comes from the general ideal gas law.
Yeah.
So if you just take a look at the ideal gas law, I think it'll be a better, because it doesn't tell you that you have to apply Charles' law. I'm just saying that that's like a way for that's like what that means. Constant pressure means you can apply Charles' law. But if you look at this, doesn't it make more sense that when your temperature increases, your volume increases?
I thought when your
Right.
temperature increases, your volume decreases.
Yeah, but then I'm trying to find like if this was our case, because this is what I assumed in the beginning. This is what I assumed, like this is gonna be, because if this goes down, then we can't really determine what ds is. So I'm trying to like justify whether this has to go up or down.
Hmm.
But now and if you're using the PV equals nRT, the volume has to go up in the end because of this temperature that's increased.
Okay, volume, temperature both increase.
Yeah.
Okay.
If temperature increases, volume increases if your pressure is constant. Yeah, it's just relating terms and terms and more terms. And then so if both of these guys like go up, that means your entropy is increasing.
Entropy
Or
is increasing.
yeah, it's greater than 0.
Why?
Because of that equation. The equation that we talked about here in the green.
The ds equals du over t plus pex dv over t.
Yeah. We're just trying to hash out like these individual terms. Like given what he wants us to do.
So p2 is increasing with b. I guess ds would also be increasing.
Yeah. This one's a little bit like this pretty much this question. I guess because it's the last one. It's like really pulling together. Do you know your ideal gas law? Do you know your heat capacity equation? Do you know the relationship between volume and temperature? Internal energy and temperature, and then altogether, do you really know how that affects the entropy? What do you think of this one?
I don't know. It's difficult for me to
Yeah,
understand why you have the answers and what is the answers for this.
yeah. Does he give you guys a solution? But for the homework, by chance?
I don't. I think so.
Okay, let's confirm them later on. Once he gives it, and then I want to see because like in the end, we want to talk about the right thing. So let's talk about this one once he gives you the solution. And I guess when is this one due?
Tomorrow at 11:30, I think.
Okay. Well, at least you have all the solutions, right? You don't have to do the exercises. So, but we'll talk about that. I'll just give you like my answers to those, and maybe if you have a question, let's talk about it. This is number 2. I did number 2. I also did number 3. I think 4 and 5. And then I think 6 to 10. I can give you that afterwards. It's not that bad. This is the one where you're really just applying it. This is probably like more of like a test problem.
So, what do you mean when you say G, F, and A? Is G
Okay.
given, F is fine, and A is answer, or?
Yeah, solution or answer. Like this is given assumptions, fine, obviously, and then A is answer.
Okay.
Like a solution set. I think you saw that in my other one, right?
Yeah, and I was actually going to mention, I was going through some of those, and they were telling me like the answers were incorrect. Um,
Okay, which
on
one?
So the first one would be problem 4, I think, on the um, thing. Let me just, it
Let me look at that
logs.
one.
Okay.
Problem 4, you said.
Yeah, I was saying that the,
This guy, okay. This
so it
one isn't that.
says,
This one isn't that bad actually. Like I was wondering how. Okay.
yeah, because it was saying when I tried to put in T, it was saying that the answer doesn't, the solution doesn't include, let me see some answer. Variable t is not defined in this context.
What is it? What is it then? Is it x?
I guess it's x, but when I try to put in, because I put in c1 plus c2 e to the negative 5x.
What did it say?
Let me just put that in again. Submit answers.
There's like no way it can be anything else.
Yeah, it says incorrect. Your answer isn't a variable equal to a formula that returns a number. It looks like a formula that returns a number. I'll go ahead and share my screen real quick.
Okay, go ahead. Maybe this is a particular solution. Maybe it's the particular solution somehow.
Okay, I'm just gonna go ahead and start the screen.
Okay, go ahead.
Okay, cool. I think it's recording.
Did you share the screen?
Okay, screen. Okay, here's that one. Share.
Because there's two answers to this question. Okay,
yeah.
A and B. Let me take a look at this one. Okay, give your answers. Let me just read through it. The answer preview. It gives you an answer preview. Okay, that's your answer, right?
Yeah.
And then so find the general solution. Give your answer as y equals. And in your answer, it's because isn't it okay, you did C1, okay. And then C2 is C2 and e to the negative 5. Your answer isn't a variable equal to a formula that returns a number. It looks like a formula that returns a number. Isn't a variable equal to a formula that I don't even understand what that means. Your answer isn't a variable equal to a formula that returns a number. It looks like a formula that returns a number.
So would it be f
the heck?
Would it be y equals or?
Hold on. Give your answer as. Oh, maybe it's y equals. Yeah, it says give your answer as y equals.
Y equals. Okay, let's see. Okay, and then I guess then the other one would be y equals.
What the hell? It shouldn't matter, but I guess it's okay. Whatever. It kind of trips people off.
It still says the second one is incorrect.
Okay, let's take a look at this one. I thought this was the one that it gives you the particular solution already. Let me take a look at what I have. So, did you go through this though, like the process at least?
Yeah, let me see if I can try to find.
Can I check like what my answers are correct?
Yeah, let me see. So, let's see. I guess I'll do.
Let me see. It is y 0 equals 1, right? Y prime 0 equals 1. I think that's like the two equations.
So this is 4.
Okay.
So it's B. So we have our two initial conditions that we determined.
Okay.
And so we determined C1 and C2. There's C2 there, and there's C1 there. And it's just plugging it into this one.
It can't be anything else though. C2 has to be negative 1/5, right? Did you put C2 as negative 1/5, or which one did you do?
Okay, wait. I think it might have just been swapped around. Good one, and then this should be 6/5.
Oh, that's probably why. You were following. You just directly went. Yeah.
Okay, great.
It's this guy. Right? Oh, you're not looking at my thing, but yeah. Okay.
Yeah, I'll stop the share. Okay.
but yeah, like I said, like the way I was writing it, I was rushing. But the C's are obviously correct. It's just the way it's like written.
Yeah.
So right here, yeah, if you went, yeah, try to like go through the process and let me know. But the process is the same. It's just the way I transferred it over.
Okay. And I think let me see number 5 real quick. I'm just gonna think.
Number 5. Let's look at this one.
Let's see next. Okay, I was just having a kind of a hard time understanding what you were writing to go through these.
Number 5?
Yeah, because it was 6. Like I noticed that you kind of wrote it like almost like in the form of a series where you had the one.
For number 6? For number 6? Of number 5? 6. Number 6 or because number 5 had a lot of things in it.
Yeah, number 5, on that one.
Oh, I see. For number 6, right? This guy. Like you're talking about like it looks like a series.
No, it was actually number 5
It was number
itself.
5. Number 5, what part? Number 6?
I mean, for number 5, the solution kind of was giving, you gave the red box and then you drew a dot, 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 and then a 6.
This guy means like I skipped number 2 to like number 5 because there was a lot of problems. But you just apply the same steps pretty much.
Okay,
Like
so I mean, I know that, so that, like, it's just the, I guess, the symbology I'm kind of confused about. So what is the upside down A?
upside down A. You're talking about this guy. This
Yeah,
guy,
at
right?
the very top.
This guy means for all.
For all, okay. And then that E is an element of all real numbers?
Yeah, but what this really means, like just to like put it in layman's terms, this just means like K, A, and B are constant.
Constant.
Yeah, this is what this means. This whole thing right here.
So that E means a constant?
This E means an element. This E right here
Okay.
means it's an element of the real
Oh,
number.
okay, so they're all 3 of those are part of the real numbers and real numbers are constant. Okay.
Exactly. Yep. Yeah.
Okay.
It's just the way I usually, because I don't like writing a lot of words.
Yeah.
But I had to do that for like the chemistry one, which kind of sucks. Anyways, yeah, like for these ones, did the answers at least, did you understand them? Or like I said, you have to do the problem. It's like there's like 3 different types,
Mhm.
and you
Yeah,
just have to do.
it was actually my mom's birthday weekend, so I
Oh man,
really,
so sorry about that. Like,
yeah,
you don't have to do this right away.
I didn't have time to actually go through these problems. So I'm just kind of trying to figure
That's
these
fine.
out near the end.
When is this one? Is this one already due?
This one's due at 10:30 Eastern, which is,
Soon.
well, no, not 10:30 Eastern. It's 11:30 Eastern. So it's due at 10:30 Central. So it's due in an hour 15.
Okay. Are you almost done? Like, it's not that bad if you did. Yeah, I know. Like, if you didn't do any of the work, it's gonna be long.
Yeah, I'm just,
You could probably. Can you guys get an extension?
no, there's no extension because he says you have 2 weeks to do it.
Okay, that's fine. Do you already have your next homework? Maybe that's why. Yeah, maybe we can work on it early.
Yeah,
I'll
so
try.
homework
I'll
5.
give the solutions. If we have 2 weeks, yeah, that's enough time.
Okay, so yeah, so the PDF or hard copy, I'll go ahead and just send that to you real quick. So, let's see.
What are you guys covering now in or this coming week? Do you know what you're covering?
No, not yet. It's like he issues stuff that is due like in 2 weeks that hasn't been covered yet. So let me just share the screen again real quick.
Okay, let me just end this one. Okay.
Just, I'm trying to
Are these
see.
like your 2 hardest classes, or like these 2
These are
classes?
really my, yeah, I have 3 classes and 2 of them are difficult. So
Okay.
I'm trying to see how I can actually, okay, here it is. Exit minimize video. Okay. Let me just go ahead and share the screen.
Cool.
Share. Okay. So.
Oh, okay. This one is
That's,
due in 10:04. Okay, yeah, we have enough time.
yeah, so this is FG and H linearly independent. And then
Wronskian. Okay, good. Something we've seen already. Okay. Second
this,
order with Wronskian. That's kind of similar to match the second order with the Wronskian of their fundament. Oh, that's like one step over what we did. This is the Wronskian of one of their fundamental solution sets. That's gonna be a long one.
suppose the Wronskian 2 functions are given by this. So the determinant.
Okay,
So,
that one, the vector. Okay, that one's fine. So a bunch of Wronskian, and then Determine the
Differential.
constants alpha and beta. This is a, is this a constant? Okay, good. It's still a constant, but this is inhomogeneous now.
Yeah, non-homogeneous.
Method of undetermined coefficient. Yeah, we could do that one. That one's not that bad.
Okay, and I'm still kind of, I guess it's real early on, but I really don't understand the previous homework informations either on
Okay.
these. So
You mean
1
homework
through,
4?
well, homework 1, 2, and 3.
Okay. Did you send those to me? Maybe I'll take a look at those.
Okay, yeah, I did. I sent them to you before.
Okay. The thing is, let me see. Maybe we can. I don't want to cover 1 and 2 and then take time from 5. You know what I mean?
Yeah.
Maybe I can do those solutions in my like free time, but then we'll mainly cover 5.
Okay.
And I think if I actually like do it step by step for 1 and like 1, 2, and 3, it'll make more sense. So I'll do that. 5. I'll give you my sets of solutions for 1, 2, and 3. Whenever I finish them, because then that's a lot. You know, doing one homework is already a lot.
Yeah. So suppose y c1 cosine kx c2 sine kx.
Suppose why. Okay, rewrite your answer to previous parts. And this one isn't. It's not bad. It's just doing this. Okay, and then solve this problem by educated guessing. Okay. Match each. Oh, this one isn't that long. Is that the last problem?
Yeah, it's 8.
Yeah, this one isn't that long. Yeah, this shouldn't take that long.
Okay. It's a lot of things. Okay. So
Yeah, I would say like, you know, we really need to. So for this one, I'll try to explain each individual step, and then for like homeworks 1. Well, oh yeah, there's another chemistry homework, right? You said this week.
yeah, that would be T7.
And when is that one due? We can. I'll definitely show you the
Wednesday.
solutions for that.
That would be on Wednesday.
Okay, and it's just for all of these. It's definitely just the critical thinking, right?
Yeah, for these.
Decide?
Yeah, for the problems themselves. Yeah, the exercises are going to be for the exam, but for turning in the information, it's just the critical thinking.
Okay. Okay. I'll give you the critical thinking for that one before Wednesday.
Okay.
And then homework 5. Well, so I'll give you the chemistry one first. For homework 5, I'll give you that after. And then maybe let's talk about, what do you want to talk about in the next one? Just which subject first? Let's talk about the math first, and then maybe, because that one is, oh no, actually the math one is not due until later. So maybe let's talk about the chemistry first. Like, because I'm thinking like maybe it's too early, so I like to have another one like before Wednesday. Or did you want to have another one before Wednesday?
Probably one. This is Sunday.
Just to explain like the other stuff for that homework.
Maybe because it was kind of, I don't know, either because I was thinking there's something due on Sunday, and then there's something due on Monday and Wednesday. So
Monday, Wednesday, you always have something to do for the chemistry one, right?
yeah, Monday, Wednesday, and Sunday, 3 things are due. So I'm guessing
which one is the Sunday one? Is that the math?
the math.
But not for this week. You don't have anything to do for this week, or is it that day already?
Yeah, it's that one. So
it is that day. Okay, so let's maybe before Wednesday we'll talk about the next chemistry, and then Saturday we could probably. Do you want to do a Saturday or a Friday?
probably a Friday would be better.
Okay, Friday. We'll talk about more about later. Let's just talk about the. So when do you want to do the chemistry one first?
So the chemistry one, maybe do that on, I don't know, Tuesday.
Okay, let me check that day first. Tuesday. Let's see. Okay, that one's not bad. Okay, yeah, we can do Tuesday. What time? I guess your time, and then
Um,
What about say not the same? I have a 2 p.m. Pacific time, but
okay.
after that I'm free.
So maybe, let's see, maybe 4 p.m. to, I don't know, let's see, 4 p.m. to,
Same amount of time. I think this time slot is good. This length of time.
okay, so 2 hours, maybe from, I don't know, let's see, so
Yeah.
maybe,
What? Okay.
so you said that you have one at 2 p.m. Pacific.
Yeah, I have like it's only for like an hour and a half. So 2
Okay.
to 3:30. After that, I'm good.
4, 6, 6. Um, yeah, it's kind of difficult because the time is, that's around, I guess, dinner, but I guess I can probably work around that.
What about after dinner?
Yes, that's gonna be,
I think it'll be good to do it on Tuesday so that like because it's due on Wednesday, right? You said
yeah, so this may be 6 to 8.
my time.
Yeah.
Oh yeah, perfect. Anytime like that during the evening is really good for me. Yeah, 6 to 8 is actually better. Yeah. Okay, let's do that one.
Okay, so yeah, it's gonna be 8 to 10. Okay.
Okay, perfect. Yeah, like do you know what these next chemistry homework? Do you guys go really fast, or is it like you
It's
guys
two
cover?
it's two sections a week.
Okay,
So
and I don't even know how far are you guys? Are you guys like this class? It seems like it's like a lot of everything.
yeah, so there's, let me just pull up the PDF again. So okay, so I'll show you the schedule real quick.
Okay, let me just end this one.
Okay.
I'm hoping that you guys won't go to. There's no heat transfer though, right? It's just thermodynamics.
So this is the kind of, this is the schedule. So we've gone all the way up to T7, which is
Oh,
going to be,
that's what the T stands for. Okay. So T, okay, and then like, oh, that's a lot of quizzes.
yeah, 10 quizzes. So T, and I have the list of, I guess, the chapters and everything. So
Chapter
T
6. Okay. What?
T7
Okay,
T7 is entropy changes as a function of temperature.
that's fine. Okay,
T8 is the third law of thermodynamics.
which is the absolute zero. Yeah, that's just zero.
Yeah.
Okay. Okay.
And T9 is Gibbs energy and Helmholtz energy.
Okay. We talk about Gibbs a little bit. Yeah, Helmholtz. We can talk about that later on. Yeah.
Yeah, then T10 is also Gibbs energy as a function of temperature and pressure.
Yeah. Yep. Okay.
T10A is Euler's criterion.
Okay. Okay.
And T11 is equilibrium. And I mean, I can go through the whole list if you
You,
want.
you don't have to.
Okay. Yeah, but I mean,
But
it's up to
what
Euler's
is
criterion.
what is 6.3? Like, or actually, what's the last chat section? What's 6.6?
6.6 is T22. That is more complicated solid liquid phase equilibria.
Okay, it's all thermodynamics. It's not gonna go over that one. Okay, that's fine. I just wanted to know, like, if this class is gonna, what's the extent of it?
Yeah, and I mean that's T23 is that's liquid vapor phase equilibria, and then but after that, then it's, I'm guessing that's going to be second semester because then you get into electrolytes, electrode potentials, and
Oh,
then
those are fun. Yeah. Okay.
K1 is chemical kinetics, and then activation energy, enzyme kinetics, things like
Okay.
that. And then M1 is mathematics for thermodynamics, but that's it.
Oh wait, you guys have a separate class for math for thermo? That seems interesting.
So 323, I mean, that's at the very, very end. I don't even know if we even reached that point in the second semester, but mathematics thermodynamics, it looks like it's just like you have a function of x and y, and you have initial final positions. It's just like
Yeah.
some calculus one stuff. What is the function is increasing? What is the sign of dy dx?
Yeah, that sounds like a fun class. It's like really computation. Maybe I don't know. Maybe you have to like because like you're learning the physics right now. You're learning like, all the physics stuff, and then like
Yeah.
you're adding. Not now. Let's add in like allow the physics with the math.
Mm-hmm.
Whatever. Okay. I think yeah, that's doable. This class wouldn't be that bad, but it is pretty fast paced. It looks like you guys will cover like we're gonna cover like 4 chapters in the amount of time. it's I don't think it's is it the whole book? Are you guys covering the whole book?
I don't know. At least for the first semester, it's not all the book. It's up to T23, so it's about half.
Okay. Okay, that sounds good. Let's I'm gonna schedule the stuff and then we'll talk about the next things on like Tuesday, and then let me know if there's anything else. I want to send you what I have today. I didn't really send it to you yet. We just talked about it, but like if there's questions in lecture, you know.
Yeah.
And like yeah, you definitely. I think from what we've done, it can work out. Like we're just doing homework. There's like 2 homeworks that we're talking about every week. 3, I think. No, right? We have to talk about 3 things every week.
Yeah.
uh, are you doing other thing? Like, are you practicing like besides what we're doing here? I think it would be good to do some practices on the side in between times, just to get like before the exam comes in. And what I mean by practice is I think for the for the chemistry one is definitely doing the exercises. Those exercises are optional.
Yeah, but I'm gonna try to do them.
And then for the for differential equations, what other resources can you like besides like the homework? Are there other problems in the book that you can do?
He didn't give any. Like usually professors will say like recommended problems.
Yeah.
He didn't give anything about that.
Bums. I would probably just like redo the problems then, because they're already hard enough, right? Like there's a lot of problems.
Mm-hmm.
Yeah, just try to redo them. We'll talk about the 5th one, before Sunday definitely, and then like just to get you up to speed on 1, 2, and 3. They're not that bad. Like I feel like a lot of the math part is not hard. It's just the process. The chemistry is gonna be the one that's more hard.
Yeah. Would it be possible to do 3 times a week?
Yeah, I mean, I'm very flexible. Like I like doing these subjects. These 2 subjects is definitely something I like.
Okay.
So, like I'm thinking that since there's 3 homeworks, we can do 3. You can do 2. Whatever, how many you want to do. Like,
Okay.
I'm pretty flexible, and I like doing the actual problems. So it's like a good thing. Like just keep on sending me the weekly problems, and then I'll give you the solutions, and then we'll talk about them, during the sessions.
Okay. Okay. So I'm kind of mentally overwhelmed a little bit. So I sent you the homework. Okay, I'll send you the homework for that's due this week.
Okay.
And then I guess then the Tuesday. So then the T7, the T8 is what I guess the T6, yeah, T6 and T7. And then you already have that information. Okay, so then.
Yeah, I think I have everything. Just like every time you get the homework, just, the 2 chemistry homeworks, you get them every week, right?
Yeah.
Just send that to me once you get them, and then the math homework, send that early because that one's long.
Yeah.
I think both of them are long. It's crazy how you're taking all these, like.
Yeah, I everything's falling apart. It's just.
No, you're good, man. Like I feel like these aren't really that hard. The more that's actually something I don't like. Like some teachers do is they'll talk about like all these theory, and then they'll only give you like 3 homework problems.
Mm-hmm.
And then you don't really get to practice it. So it's both bad and good, but I feel like in the end you're really gonna learn more about the subjects more than your other peers.
Okay.
Like
Yeah.
if they were to take it from another professor. I always take it that way. The more problems you have, the more ready you are.
Mm-hmm.
Okay, and thanks, man. And then I'll see you on Tuesday.
Yeah. So can we do Tuesday, Thursday, and Sunday?
Tuesday, Thursday, and Sunday. Yeah, we can do that.
Okay, great.
Tell me the time on the other ones later on.
Okay. Yeah, I mean, I pretty much am available at the same times. So
6.
Yeah, 6 to 8 on Tuesday, Thursday, and Sunday. in your
Yeah,
time?
actually, yeah. If you don't mind, yeah, let's make that the time, because as I said, like I don't really like this time doesn't really matter, but mornings are not fun for me because I'm doing other stuff.
Okay.
Okay, cool. Have a good one, man. And then like what I do best is like, always try to do the problems, but then take a break so that you don't get overwhelmed.
Yeah.
Yeah. Have a good one, man.
You too. Thank you.
Yep.